Hi guys, so we've been taking a look at inductors and we've been able to establish a few things. One major thing that we were able to establish was the IV characteristics for an inductor. We were also able to establish the energy storage capabilities. In particular, we found that the energy stored in an inductor was stored within the current and associated magnetic fields. Uh, there's one last fundamental property of inductors that we need to explore before we continue with other material, right? Now, I don't want to give away exactly what that property is, so let's just go ahead and start discussing it. So there's a fundamental property of inductors that we really want to explain. And I want to begin this with a question. And the question is, in an inductor, can we have an instantaneous and discontinuous change in the energy? So, for example, suppose we were to analyze this question graphically. And suppose that we had graphed the energy in an inductor versus time. So here we have our two axes. We have time over here. We have the energy. And suppose that we were monitoring the energy in the inductor, and it looks something like this. And at some time, one of the things that would happen is you get this, at this time, this kind of jump discontinuity. So it has one value at one time, and then it doesn't go through all the rest of the values for later time. It just jumps in one door. Right. Now, to answer this, I want to go back to a definition that I'm sure most of you guys remember, and that's the definition of power. Right? The power is the time rate of change of the energy, like this. And notice that at this particular point, when you actually have that discontinuous jump in the energy, well, the derivative of this with respect to time, notice that it's not defined, right? So over here, at this time itself, which is the time derivative of the energy, it's not defined. It's even worse, it's actually infinite. Now, in order for there to actually be this jump in the energy, notice that you would actually have to either supply an infinite amount of power or an infinite amount of power would be supplied by the inductor. This is clearly not physically possible. You cannot have an infinite power, right? So, because the physical constraints, because you cannot have infinite power, the energy inside of an inductor must be a continuous quantity. And I'm underlining must. So it must be a continuous quantity. Now, the major result comes from what we did previously for energy storage in an inductor. So recall that inside an inductor, the energy instantaneously is 1/2 the inductance times the current squared, right? Now, if this side is continuous, and you have these two constants, then it must be the case that I squared must be continuous. So from the definition, or the result of how these inductors store energy, we can conclude that I squared must be continuous. And if I squared is continuous, then I, which is a function of t, must be continuous as well. And this is what we actually wanted to get to, is that an inductor current must be a continuous quantity. This is the important result. This is what I wanted to circle. So in your circuits, there might be a lot of crazy things that are actually happening. Right? However, suppose that you actually take a look at the inductor and you find that the current at a certain point has, let's say, a value of 1 amp, and later on it has a value of 3 amps. It must have gone through all of the values in between continuously. It cannot discontinuously jump from one value to another. And that is one of the fundamental properties of inductors, and you'll see how this money gets used, or this piece of information gets used later on. Right?